Alright, in the last video we solved this repeated root second order differential equation here, and we proved why we could just take our linearly independent solution and multiply it by t to get a second linearly independent solution. Well, I'm going to show you another way to figure that out using a technique that's actually pretty good, and we're going to use it for other things, called reduction of order. The method of reduction of order says that if you have one solution to a differential equation, you can guess a second solution to a differential equation by taking the first one and just multiplying it by a function of the same variable. Typically that function is going to be called u. What we're going to do is we're going to take derivatives and plug this into our differential equation to figure out what u has to be. So since u is a function of t, and obviously this is a function of t as well, we're going to have to use the product rule a couple of times. I'm going to drop the of t because that notation is going to get a little bit annoying. Again, we're going to start plugging our guess into the differential equation. And something cool is going to happen every time you do this. You'll notice the u terms actually are going to cancel each other out. In this particular example, you have a couple more terms canceling. You have u prime terms canceling as well. And what you're left with is pretty simple. Obviously, e to the t is not going to equal 0, so we can just cancel that out. And you have u double prime equals 0. U double prime means two derivatives with respect to t, so you can actually integrate. If you integrate once, you're going to get u prime is a constant. If we integrate one more time, again with respect to t, you get u equals c times t plus some other constant. I'll just call it d. Now this is actually great. We have everything we need now to find our second linearly independent solution, y sub 2. We know that y sub 2 is u times e to the negative t, and we just figured out what u is. And now it's great because we have two linearly independent solutions, but this can actually be simplified, and here's why. I'm going to write down the general solution. You know by now that the general solution looks like c1 y1 plus c2 y2, and that looks like this. Okay, so this is our general solution here, but it's got a lot of constants floating around in it, doesn't it? Now I'm going to group the e to the negative t terms together. And now look at all these constants. All of these, c1, c2, c, and d, are all just arbitrary constants. They came from integration. So we have an e to the negative t term with some constant in front of it, and we have a t e to the negative t term with some other constant in front of it. So what we have is a constant times y1 plus some other constant times this thing right here, so we may as well have just called that y2 from the very beginning. y1 is e to the negative t, y2 is t e to the negative t. So basically what that means is we could have just gone all the way up here and said, well, we don't really need these constants, so we can just call c equal to 1, and we can call d equal to 0. And that would have immediately given us the simplest version of y2, which is just t e to the negative t. Okay, let me run through what we just did there because I know that was a bit much. The method of reduction of order. We're always given one solution to the differential equation, but we want to find a second linearly independent solution to the differential equation. So we actually guess the first solution times some function, and the goal is to figure out what that function is. So we take derivatives, we plug those derivatives into the dE, and we figure out what u has to be, and that gives us y2. And typically we can make a simplification where these constants don't really matter, so we make them as simple as we possibly can. Let's do another example, and this example will show you why it's actually called reduction of order in the first place. Here's example 2. All you want to do is find the second linearly independent solution to this differential equation, and you're given that the first one is t. Again, we're going to make a guess that our second solution is some function times y1. I'm going to take derivatives, plug those derivatives into the differential equation. Again, these are implicit derivatives. We use the product rule to get those. Now let's plug them into the dE. I'm going to distribute through the parentheses. And as always, you'll notice that the u terms are going to cancel out. If those u terms don't cancel out, then you've done something wrong. I'm going to combine like terms. And now, because these u terms canceled out, we can actually make a tricky substitution to reduce the order of this differential equation. I'm going to use the substitution v is u prime. If we do that, we get t cubed v prime plus t squared v equals 0. And now we've reduced the order from a second order differential equation to a first order differential equation. This is a first order linear differential equation that is also separable, so we can do it either way. Let's solve for v. I decided that I was just going to separate, so now we can integrate. Now if we exponentiate both sides of the equation, and we can use just a little bit of algebra. We get a solution that looks something like this. Now, in the very beginning of the problem, we actually wanted to find y2, didn't we? And to find y2, we needed to figure out what u was. And to find out what u was, we had to use the substitution v. So we need to get back to u, so then we can get back to y sub 2. I substitute v is u prime, and then to find u, all you have to do is integrate with respect to t. And now that we have u, we can find that y2 is just u times t. So that's just y2 is at natural log of t. And again, this constant here doesn't really matter because when we plug this y2 into our general solution, we're just going to get another constant in front of this thing anyway. So we may as well just call y2 t natural log of t. Okay, I hope this video wasn't too long. Here's a quiz for you. I want to use this same technique, reduction of order, to find y2 given y1. Good luck, and I'll see you in class.